Okay, so hello everyone. Uh, I hope you get the basic concept for um, area between curves. I think your TA left some questions for you, right? Right. Okay. So um, does anyone solve the question? I think some of your TA they already solved the number 1A and B. But let me review, okay? So if you have the functions cosine pi x, and then the other curve is 4x squared minus 1. I hope, okay, in every curve that you will get in integrations, you can at least draw the curve, okay? Draw the curve correctly. Find the intercept, find the, maybe if it is the polynomial, you want to find maybe which is the maximum minimum value, you can apply the chapter 4 calculus to find the maximum minimum value, at least to see whether the curve is concave upwards, downwards, or both. Okay, and you can derive equality 0, find the critical point, etc., and so forth. And you can also check the second derivative if you want to make sure the curve is correct. But usually in the integration, if you see the textbook, the questions for the curve, usually the curve is not too complicated. It's quite as simple like this one. And other typical curve, like maybe 1 over x, or maybe a square root of x, you need to imagine how it looks like, okay? And then the other point in area between curves is finding the intersection in which the curve will intersect each other, in which point, and that usually that will be your point of integration. Usually depends on your perspective, because you can integrate with dx or dy, right? It depends on you which one you prefer, or which one is easier to integrate. And here, because cosine is easy and predictable to graph, you can start the cosine by the stating the maximum value is up there. The cosine maximum value is 1, right? And then if we're getting 0 at half, because cos pi over 2 is 0, right? And you can get the intersections between the negative half and half. That is when the value is 0. And then you can just using the idea for area between curves. Every curve that is above the other will be the one on the left. So the top minus the bottom. Okay, that will always be a concept for integrations. And also for dy, if you integrate dy, the one which above, but you need to see from different angle, right? You need to flip, to switch the axis to see which one is the top one. Or if you want, you can say the one who are in the right minus in the left. Okay, that's all the area between curve concept. How you find the area. Okay, how you are minusing the which curve minus which curve, right? Okay, so here the top one is the cos pi x. If we are looking at these integrations, so we are looking, basically we are looking this rectangle. which is this is the dx, and this height is the difference, right? The red color, the cos pi x minus the 4x squared minus 1, right? The height difference, okay, like this one. Okay, so we are actually multiply the dx multiply with the height, right? The height is the difference between the curve on the top and the bottom. Okay, and mostly whatever in the area between curves, this is always the basic constant. Okay, so basically there's uh, no complicated like formula or whatever. It's quite simple. The difficult one is if you have like special restrictions or special functions that you need to think of, and then if you have, because it's direct approach, right, from here until here. Okay, but in other case, maybe you need to stop here, and then maybe you need to look at the restrictions if the question have restriction. Okay, so you can get the answer, solving, integrate. Uh, as a reminder, if you have cosine and you have a constant inside, like for this case, it's pi, right? If you want to integrate, cosine integrate becomes sine, and don't forget to over pi. To make sense this, imagine this part, you derive sine pi x over pi. It's cos pi x multiplied by pi, right? Pi and pi here will cancel, and it will be the original one, right? So that's how you are how you confirm your answer. Okay, why we need to write the constant at the bottom. Okay, and then you get the answer. Um, yeah, only 2 over pi minus 2 over 3. That's enough. You can stop here, and then this is your final answer. Or you can stop here. That's also fine. Okay. Or if you are lazy, you stop here. For me, that's still okay. For me, that's still okay. And you want to skip to other questions, that's fine. That's fine. Okay. That's number 1. Uh, do you want to write first? Okay. And also to remind you that next Thursday, uh, we will have quiz. Okay. Quiz for chapter 5. Okay. Chapter 5. From the Riemann sum, the use substitutions. Okay. Uh, the fundamental theory of calculus also. Okay. And maybe on Tuesday, I will do some review. So I will continue maybe around 20 to 30 minutes, continue chapter 6, and then the rest will be chapter 5 review. Okay. And hopefully next 2 weeks, we can start chapter 7. Maybe 2 or 3 meetings, we can finish chapter 7 and then go to chapter 8. Chapter 8 is short, not really that uh, complicated. Only two sections that I will consider. Okay, let's continue the other question, number 2. Okay, number 2. Now we have cosine x and sine 2x, and the x start from 0 until pi over 2. Now to draw or to understand the sine and cosine graph, you need to understand the uh, how the graphs look like. Like for example, if you have the angle twice than the original, what will happen, right? The original sine, it should be uh, yeah, it should be this one cosine. Yeah, the original sine should be here and goes here, right? It goes here. So whenever you have uh, multiplications on the angle, like 2x, 3x, 4x, meaning you are the period. Okay, remember the period in physics is become smaller. Okay, the periods become small. Or you can check, use the easy angle, pi over 2 or pi. So try pi over 2 goes there, it's pi, right? Pi is 0. And pi over 4 to become pi over 2, and it's become 1 here. So the maximum is here. So we get from here to here. That's the sine. And cosine is still the same, like we always know the cosine. And 0 is from here. This is 0 until pi over 2. Now we have one area here and one area here, right? And we need to make two area, right? Area 1 plus area 2. Two area. We need to plus this 2. So this is A1, A2. Okay. Also, if you want to check the intersections, you can check the cos x and sine 2x, equaling both of them. You get the sine x equal half, and x will be pi over 6. So this point here is pi over 6. So integrations, if you want to look at the x, you go from 0 until pi over 6, and then from pi over 6 to pi over 2. So this area 1 from 0 to pi over 6, area 2 pi over 6 to pi over 2. Okay. And then, yeah, we have this area 1 and then area 2. Okay. Area 1, cosine x is above, right? And area 2, sine 2x is above. So cos x minus sine 2x, sine 2x minus cos x. And you can make some calculations here. And you will get the answer is, yeah, half. I think uh, not too complicated, right? So let's you want to try write this first? Or maybe any questions so far? Any questions? No? Good. Okay, let's continue. Now, um, now you have the curve 3x minus x squared, y equal x, and then x equal 3. So this is y equal x equal 3, and this is the 3x minus x squared. If you are maybe not sure how to draw, check the first derivative if you want, okay? And check this is become the critical point, okay? And now it's become maximum value. So the graph should be like that. Okay? Maybe if you confuse like in the exam, if you have minus x squared, the curve is this or this. Maybe you confuse. You can try this one, make it 0, put the critical points, try the some number here, and it become positive, negative. So it's going up and then down. So it should be maximum, right? So every part in the first half of the calculus, the derivative part, you will still need in the at least to confirm the integration, you need derivative. So do not forget the basic derivative, because if you do not remember the basic derivative, then the whole integration will be difficult. So try to if you feel uh, maybe having difficulty in the derivative, you need to look back and try some, maybe take some exercise, or maybe relearn the concept, okay? Because all the concept will be bring it, we will bring it on the integration. And also all the concept in this semester, we will bring it on the next calculus. Okay. Okay. Now we have this curve. Okay. This line, right, and this line. Now the question is, what is the area between the three curves? Sometimes I've seen in the exam, this is questions, the students will answer, oh, here and here. Do you agree? The question is specifically asking the curves on those three. So only three curves. Okay, so all three curves must be included. If you see this curve and this line, this one, okay, this part is not included, right? So that's not our area between curves. We need to include all three. So 1, 2, and 3. So only this area. Okay. Except the question is asking differently. Okay. So if this kind of questions is on your exam, if you feel confused, please ask. Okay, to make sure the question is understandable for you. Okay. So please ask if this is all just 3 or all possible. If it is specifically only 3 curve, then this is only the area. Okay. Yeah. So first, you can check these intersections, and this, I think this 0, right? But we need to know this, so we can check on the these equations become the quadratic functions, right? And we can factorize. We can check it's 0 and 2, so it's correct. It's 0, and the other one is 2. So that's for the x. And then the area will be integrations from 2 to 3. Okay. And the above equation is just y equal x minus the parabola curve. Okay. And you can solve it, and you get the answer is 4/3. Okay. Okay. Any questions? No, I think still not too complicated. Okay. Now a little bit difficult. Not too difficult, but you need to at least to understand the question. So find uh, the area bounded by parabola y equal x squared. I think you can draw that easily. The tangent line to this parabola at 1 and x equal 1 and y equal 1, 1, 1, and x-axis. So the area is between three curves, okay, at least three lines. The first is x squared. The second is the tangent at 1, 1. The third one is x-axis. So tangent line, the problem from derivative, right? Just find the first derivative and find the value. What is the value of the tangent? So first derivative and then put in x equal 1. So the y prime is 2. So or the gradient is 2. Okay? The gradient is 2. The slope is 2. And then you can check the drawing. Not to quite proportion with the tangent. It should be really at this one point the tangent. But yeah, let me marks this as 1.1. So the tangent is on this point. So this is the x squared. And this is the tangent. Now, the area now, this x squared, the tangent, and x. Okay. So it's close at this area, and close as the area. Okay. You can check, okay, make the like this rectangle. Check if you are using the X. Okay. Check the rectangle. Put here. Is it fit with your integrations or not? And which one is easier? If you are using this, then I think at this point, you need to have separations, right? So I think we can use the other rectangle, dy. Because if we are using dy, it will perfectly fit, right? If we are using x, it's not perfect here because you are having this. Or you can have this all minus this and you still get this. That's still fine, but takes a long process, right? So let's just take dy from here until the 1, right? Okay, so this is the tangent line. So you are putting in the line equations. This 2 is from the slope. 1, 1 is our point, 0.11. Okay, so we are getting y equal to x minus 1. And because we want to use dy, change all to so x equal y plus 1 over 2. And the x squared becomes square root of y. So we will have these two curves. So uh, square root of y minus the line equations. Oh wait, the line, sorry. The line equations minus the square root of y because we are using dy. Okay. So again, if you are confused dx and dy, whenever you have dy, you need to move your head like that. So this becomes the above one and this becomes the bottom, right? And we calculate the integrations. Calculate the integrations, and we get, yeah, you can solve this. Yeah, I was also too lazy to calculate. So yeah, you can solve it. Okay, any questions? Because I believe to determine using dx or dy, that's also a key point in solving the problems. Okay? If you are maybe using dx, but you are doing it like not really correct, maybe you are like, for example, this one, you can do dx, but you need to stop here. So from here, you need to find, so this minus the 0, right? And then this minus this from here. So you need to find the point first if you want to use dx. Okay. But if you're just dy, you can just use it directly because there's nothing cut through, right? If you're using dx, because this having this x, this is a problem. Okay? But if there is no x, only like this whole curve, dx is easy. Okay. 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 One more questions, and I think this is quite complicated. Let me give you some time for you to think the questions first. So there is a line. Okay. The line goes through the origin 0, 0, and it will divide. So the line will divide the region bounded by parabola. It's not too difficult to draw, right? X minus x squared, and then x-axis. So the parabola and then the x-axis, okay? Into two equal regions. And it's asking what is the slope of the line. So the line should be having a specific slope, okay? So it's like you have the so from 0 here, and x minus x squared is, let me draw 1 here, because if I make 1 here, it's too small, right? So maybe around like that. And then it said that the first sentence, there's a line through origin. So through origin, this origin, okay? If you don't know what origin means the 0. Okay, 0, 0 is origin. So it goes through so of course, if you have line goes through origin, the line will be y equal constant x, right? Let's just say m because we want to calculate m. And this become so the area, this whole area, let's say A1 and A2. So it say A1 is equal A2. I believe you can solve it. Yeah, you can solve it. If you think like there's too many variables, don't worry. I think you can solve it. Or if A is uh, A1 plus A2, and A1 A2 is the same, so A is actually, we can also say half, or A1 is half A, right? Because this is the same. Let me give you some time to think and try. So if you have like typical questions, like in derivative, if you find any specific points that maybe the questions doesn't really say anything about that, but you need that point, you may just write, like for example, this intersections, maybe just giving A or B or C, okay? And then use the A inside your calculations. Yeah, I think the answer should be not really a perfect number, but I think a fractions with irrational. Okay, that's right. Okay. Hmm? Apa? Enggak, pakai X aja bisa. Hmm. One minus cubic, not square, but the form is similar. Okay. Yeah, I think the calculation is okay. Yeah. Hmm? Yeah, I forgot, but there's some square. Yeah. Do you understand the question? Do you understand the questions? Mm-hmm.
Bisa gini nggak? Area area ini sama dengan kedua dari.
Iya, bisa.
Jadi ini benar nih.
Setengahnya. Bisa, bisa.
Jadi kalau ini udah selesai dapat M-nya. Bisa nggak?
Ya, coba dulu dong. Kamu nanya-nanya belum coba juga. Bisa harusnya. Coba aja. Harusnya nanti satu minamnya masukin di ininya kan. Bisa aja sih harus. Gambar. Gambar kalau dia perfect nggak ada kayak apa? Kayak ganjelan gitu. Kayak tadi kan ada tiba-tiba dia berdiri lurus kan. Kalau dia perfect ngikutin si kurvanya, ya udah pakai itu gitu. Tapi kalau pas kamu gerakin dia ada ganjelan di antara itu, berarti kamu mesti bagi dua. Sini sini. Coba gambar yang tadi mana? Yang sebelumnya ada nggak? Nih. Kalau kamu pakai X. Kalau ini cuman ini sama ini kan lancar kan? Tapi ada X-nya. Jadi dia nggak bisa lurus. Nggak mesti tengah, pokoknya ada di tengah, ada yang ngalangin pokoknya. Ada ganjelannya di situ. Get it? The answer 3, right? Okay. You find? Yeah, but it has like cubic. It has a cubic. Yeah.
Itu sama dengan ini luar juga. Dari ini sama dengan ini.
Bisa. Bisa ke situ, bisa juga, tapi itu kayaknya panjang.
Panjang. Iya, panjang.
Bagusnya di kalau kamu cuma punya ini gampang kan nyarinya kan?
Iya, dua.
Ini kan udah dapet nih konstan kan?
Iya.
Ini berarti setengahnya kan?
Oh,
Bisa juga gitu, lebih cepat. Slope, gradient.
like where? Like in the ground where? Like this one?
M, you know M?
Yeah.
Have like this is y equal x, right? M is 1. We have 2x, right? And we need to find the constant M.
So it's just a number.
Hmm?
It's just a number. It's cannot
Yes.
show.
Yeah, it's a constant. Yeah, it's a constant. Yeah. Okay, I think several students already got the correct answers. So, okay, this is the graph. And if you want to know the critical point is half. Yeah, it's not too important, but in case you want to know it is half. So I draw it like this. So this A1, A2, and firstly, okay, you can see that we have A1 and A2, right? A1, A2, maybe the first thing you did is, because it's equal, you can have these integrations, right? Until some A here, and then it's equal the other part, these integrations, right? And this. And it has this triangle plus this, right? I think you can do that method, but you will have like a lot of variables to check, right? The other way, you can think this whole x minus x squared, okay, as the all A1 plus A2, right? If you just have x minus x squared, integrate from 0 to 1, and you can get easily the integrations, right? So the total here will be, it's 1 over 6, okay? So A1 and A2 is half of this, right? So it's 1/12, okay? So A1 or A2 will be 1 over 12. And then what we need to do is we evaluate from 0 to A, this minus mx, right? The parabola minus mx. So we plug in x minus x squared minus mx. And try to solve and grouping all the x and x squared, and then integrate, become x squared over 2, 1 minus m minus x cubed over 3, and then you need to put a and 0 to the inside. And then, actually, on the other hand, the intersections here is actually 1 minus m, right? So that is actually our a, right? our x. So we can substitute a for 1 minus m, and we plug in, instead of a, we plug in 1 minus m to the equations. Okay. So 1 minus m squared multiplied by 1 minus m is 1 minus m cubed over 2, and this become 1 minus m cubed over 3 is equal 1/12, half of the total area, right? And we solve it, we get this. Yeah, and then we get the, 1 minus m equal 1 over square root cube, square cube 2. M is 1 minus 1 over cubic root of 2. Okay, I think I will leave the examples like for the area between curves with your TA, and maybe if we have time to review, we will review one more. I will move on to the volume for the chapter 6. Okay. So basically, volume and area both have similar approach. Okay? Similar approach. You need at least to draw, to imagine. At least for volume, not drawing all the 3 dimensions, but drawing the 2D projections. You need to check the intersections, how you are dealing with curves, draw the curves. Okay, similar approach. Any questions from this part, or too confused about what to ask? Okay, if you have a question later, you can ask me. But let me move to another section in chapter 6. So still chapter 6, but now we are moving to volume. Or we call it's called the solid revolution. So basically, if we have, okay, like from the last example, if we have the curve here, let's say this is our curve, like from the previous one. Okay, let's say this is a curve. Imagine this curve, you have area, right? You have area under curve. Rotate the curve along the x. So you rotate here. Imagine that. Okay. So if we rotate here, you will have, let me draw the projections. It will have like maybe like a sphere, but not sphere because you have like something sharp here. So you're dealing with this. So if we have this is the dx. If we have the rectangle here, and you move or rotate the rectangle, what will be the shape of the rectangle if you rotate with X? Huh? What kind of shape? I think, huh? Huh? Half circle? Not really circle. It's like, disc, like DVD. Yeah, like that, right? Because it's not having anything here, right? So only this rectangle. So imagine, and it will be like a disc, okay? And the center of rotation is here. And then for disc, okay, for this disc shape, it's like a tube, right? But the height is quite small. The height is dx, right? But the volume is just the area multiplied by the height dx. So let's say this is the a. Let's say this ax. So ax multiplied by dx is the volume, right? And that's actually the concept for volume. Before I write some words that may be too difficult terms. So I'm imagining the disk first so that you can imagine what will you do in volumes. So how to find the area? The circle, right? Area of circle is pi r squared, yeah. Just use pi r squared here. Now the question is, what is our r, right? It's the height of the function, correct? This is our r, right? And it will be changing alongside the function. So r will be the function. Is it quite easy to understand? Easy, right? Okay. Now let me use the more sophisticated drawing. Uh, okay, so depends on the functions. You can have any shape of solids. Depends on the function. For example, this is just a random function. So basically, what we did, if we have observation from A to B, and we will observe this. This has become our endpoint, okay, of integrations. Then this is the whole area, right? The area. And if we are cutting all with some small distance in gap, that will be dx. Then the definitions will be um, let the S, okay, is solid between A, B. If, okay, the cross section of S in the plane, let's say the plane is px through x and perpendicular to x-axis. Uh, is, let's say the definitions is AX, where A is continuous functions. So we back to the very first concept. We need to have the continuous functions. Then volume is limit as n approach infinity. Okay, this by definition. So this is basically what I did before. Okay, so we can have a conclusions that to find the volume, we need to find the cross-section area multiplied by the dx from our endpoint. Okay. And basically, this part, the middle part, is the same definitions from before, from the area, from the first integrations, is always the same. Now the difference is because we are rotating, usually we are rotating with to some center of rotations. It can be X, it can be line here, it can be line here. Doesn't matter. The concept is still the same. The area multiplied by dx. Dx is actually the height of the tube, the disk, right? Usually we call this also solid revolution. Solid revolution. You have area and you rotate the area and become solid. And if you use some software, maybe I forget the name software, but usually now students mostly use that software. But in my early years, I'm using the Autodesk Inventor. It's basically when you want to make a design, like from 2D projections, so you create the technical drawing, right? For example, you are making like this shape, and you have the some like this is a half circle, this is like rectangle, and you can have maybe centering from here or here, maybe here, and you want to extrude this this drawing, extrude to here maybe. So we are rotating through this point, so you can have that, and then you will be like having like like a like a donut, right? So it's quite actually it's the volume is quite useful if you feel uh, how to rotate, how to work with that range, because when you deal with some software that deals with how to project the 2D to 3D, when you draw in a technical drawing, all the drawings should be in 2 dimensions before you translate to 3 dimensions. Like everything, like from this building, when you draw the technical drawing, all the drawing should be in 2 dimensions with this specific metric, and it should be correct measurement. And then later, you give the technical drawings to another part in the other department, and those department will translate the technical drawings into 3-dimension object. Maybe you dealing with the if you deal with more to design, maybe you deal also with the like the architect. But mostly if it's the industry, buildings for office, you will need at least civil construction, mechanical engineering, okay, to deal with that. And if you have like process to deal with, and you need the chemical engineering, because you need to think how you get the like the process and which chemical you are using, how to distill the chemicals, how to purify the chemicals. You need also to put into the drawing. We call that the process PID. What's called? Yeah, process something like a blueprint, and then you give to other department, give to so all the department will work like together. And I think all the calculus steps, like from derivative, integrations, and how you visualize with graph, it will be really useful in if you are graduating from university. Okay. So back to the volumes. So another way to see, let me copy some graphs. First one is this. Let me make it bigger. Okay. So this is what I stated before. Okay. So we can have several cuts, okay, in the solid. It's the same definition as the Riemann. Okay, we have xi, which means the sample points. We can check the sample points, and we can imagine the if we cut like with this gap, we can have these solids, right? And the gap in between will be the error, right? The error, and this is estimation. So I think most of the computational software, they are using the same logic with this. Okay? They will estimate and make the cut and make the error as small as possible, and that's how they calculate, they use the computational intelligence to do that. I think most of the software, they are using the same process. So from A to B, and it will be having from x0, x1, x2. Okay. Now another thing, this volume also can prove some geometric value or geometric formula. Like for example, the sphere. Sphere. What is volume of sphere? The volume. 4/3, right? Pi r cube. If we look at, let's say, the circle is symmetrical. I'm drawing not too symmetrical. Okay. I think still not symmetrical. Maybe here. Yeah. Okay. Let's say we have a circle, and I can rotate the circle here or left, and it becomes a sphere, right? Let me define some variables or some constant here. Let's say the constant is r. This is minus r. And we have, this is also R, right? So if we have some y here, okay, and the same as before, this rectangle, let's rotate. Okay. Let's rotate through the x-axis. And this is the x. Let's say this is x, and this is will be dx, right? And then let's define the relations between x and y and r. Okay, so y x squared plus y squared is r squared, right? Now, because we are using dx, let's define y to x. So y squared will be r squared minus x squared, and y will be square root of r squared minus x squared. So the radius of this disk, okay, let me draw the disk for you. This will be y, right? So the area will be pi y squared, right? So if you want to evaluate all the point from negative r to r, we are evaluating from here, right? So imagine the disk will change alongside this curve, right? The curve is the circle curve. We define the circle as y equal square root of r squared minus x squared. It's from x squared plus y squared is r squared, right? We define this, and the disk here, do not confuse this radius with the radius here, okay? Different. So the radius here is y, right? So pi y squared is the area, right? And let's put the volume. Let's write the volume is integration from negative r to r. So r becomes our fixed constant, okay? And then let me write this is ax because I'm using dx. You can use the dy also and you change all to y. But I'm using the x instead. And then we can write this as ax is pi y squared, but we can change to r squared minus x squared, right? From our relations. And then we can write this. And then if you see from negative r until 0 and 0 to r is symmetry, right? So I will only use this half. The other half is the same. So I will just multiply by 2. But evaluating from 0 to r because it's symmetry. Okay. If you want to calculate negative r, that's fine. Up to you. But I always make mistake when dealing with positive negative. So I'm suggesting to just using the symmetry. So pi is just a constant. We can just move out, and then we can just um, evaluate r squared x and then x cubed 3 from 0 to r. So 2 pi, and then plug in r. So r squared x become r cubed. This is r cubed 3. This will be what? 2 over 3 r, right? So volume is 4 over 3 pi r cubed. Okay, we prove the geometric formula for volume of sphere. Okay, so this type of questions, sometimes it's on your textbook, maybe the middle or the last part. You can check the chapter 6.2 volumes here. Usually they will have some geometric formula. Okay, you can have um, some variations. Maybe it will have the exact problem like proving the geometric formula, or maybe they have another restrictions and find maybe another relations. But usually they will have some formula and not really a number, not really a number. Any questions from here? I think if you deal with this type of questions, you need to first to differentiate which one is your constant and which one is your variable. Okay, the r here is your constant, pi also constant, so treat them as a constant. Okay, usually usually you can like, because it's not a really exact number, maybe sometimes we will have a confusion. Oh, what should we do here, right? So basically you need to fix the r as your constant, and then x is your variables. Okay. Uh, any confusion here? No. Okay. Let me give you some time to think first. Okay. Basically, the questions is I'm not stating any specific question, but this question is actually proving the formula of sphere from integrations. So how to prove that, and we can prove with the integration of dx. You can actually try for dy, but I think it's just changing the x to y because it's complementary, right? So this is proving geometric formula with integration. Okay, let me give you another find volume of solid obtained by rotating about x axis the region under y equals square root of x from 0 to 1. Okay, I'm giving you from the very basic questions, and then maybe we can try another questions. Okay, so I think it should be not too difficult. So because it's only from 0 to 1, maybe I make the 1 here. Okay, maybe like that. So this is until here. And we need to rotate the curve about the x-axis. So rotating here. So if this is the rectangle, the x, then you will have this is your disk, right? Okay, then the volume is just integration from 0 to 1. Let me write a x dx. This phi, and then the r will be this height, the functions. So r will be the square root of x squared dx. So volume phi x dx, and it should be phi. So this should be pi over 2. Okay. Okay, the other example. And now you have 1, 2. Okay. Let me move the questions to the next page, so it will be much clearer. Okay. Okay, to solve this, basically you need to draw the 2D projection. Let's say the line y equal 8 is here. Okay, it's x cubed. This is x cubed. So this is the curve. This is the line y equal 8. And the other part is x equals 0. So here. So the other part of x cubed is not included because we need to rotate this through here. Okay. That's our rotations. So you will have the mirror images like this, and the disk will be like this, right? Okay. Now the radius of the disk will be this, right? Now we need to use dy. Okay, this is dy, right? And this is x equal something. So we need to rewrite the functions in terms of x. So x will be square root of 3y. This will be dy. So the integrations, the volume is integrations from 0 to 8, right? From 0 to 8. The area will be pi. The radius is square root, cubic root, and then squared, and then dy. So volume, let move the pi outside. 0, 8. Let me write this as 2 over 3 dy. So volume will be integration of 2, 3 plus 1, right? 3, 5, 3. And 3 over 5. From 0 to 8. So pi, so 3 over 5. So 8 cubed is 2, 2, 5, 32. 32. 32 minus 0. So it should be 96 over 5 pi. Okay. Okay. So in summary, okay, this is all the basic definition from the beginning, the volume. We call all this method is disk method. Okay. So the idea is if you have functions and then you need to rotate the function here, and you will have the disk. If this is A, B, So volume will be integrations from, let's say, x to a, if x is a, and b is pi, and then if this is y, then this is y squared, or maybe let me write uh, y equal f of x. So this will be f of x squared dx. So this first case. The second case, you have maybe like that and rotate here. So you have this is your disk, this is y, this is x. So this is x equal, let's say g of y. If this is, let's say, c and d, then the volume is from c, d, by g of y squared dy. So the first case is dx. Okay, you're rotating through the x, and the second one you're rotating to y. Um, the center of rotation, by the way, okay, I'm giving you the example always the x or y, right? The center can be anywhere, right? You can move it, so the radius will be different. Okay? Maybe I will give you another practice, but basically now I'm just showing you that we will have two methods in this method. The other method, I will give you just briefly. Uh, let me write the problem, or let me just give you the drawing. So this is the y equal 2x squared minus x cubed. So find volume of the given curve and enclosed by the x0, x2. Rotate about the y-axis. So you have this uh, polynomial 2x squared minus x cubed. So imagine this rotate. Okay, what the shape will be. Huh? Yeah, like I think somewhat it looks like when you wash your hand. Okay, imagine that. Yeah, like that, right? like sink, yeah, for when you wash hand. Okay. So if you try with any like you try the disk, okay? Try this rectangle here. This having a hole here, right? So the disk method will not working. Will not works this in this method. So we will go by the name for the method is the shell method. But I think I will uh, go through the shell method maybe next Tuesday. Or sometimes other textbook call this is washer. Because it's like a washer. Okay. I think I will finish until here. I will continue this method next Tuesday. Okay. And next Tuesday, don't forget to bring your midterm results. Okay. Huh? Oh, you want? Yeah.
I think this is an area, right?
Mhm.
And long circle should be this. And I found only difference two away. And these two functions. This area and two away.
Yeah, yeah, yeah,
This
yeah.
10. And
Yeah.
I only just extend this.
Mhm.
But this is only difference.
Mhm.
Do a set. This volume. Integral area first, then but
Yeah, you need to find the parabola here and integration from here to here from this parabola and then rotate. Actually, once you do that, yeah, it's difficult in the form. Actually, the volume is already with the area. Yeah, the volume is already with the area. So it should if you take this method to simplify our area. I don't think if you are rotating directly from this area and then you rotate the axle, then you can translate the picture to the form of you know, so if you draw
So if you have this, you already have the area here. It's actually our definition for the area is already fx dx, right? So we find the area here, all the area. But the volume is actually the concept is the integration of the area itself, and the area is by the function itself. So actually we are already doing the area inside the volume. So that's why we are separate area and rotate. We need to going back to the original definition. That's why I'm telling you the first concept. We call this volume is solid revolution, because the solid can be formed from revolution. So basically, what I think what you mean by the area is if you have the area, maybe this area rotate and then the other one here rotate, right? You get it? And it's rotate, and then it should be making the same solid. But anyway, the volume is already fixed with the area and then the height of the base. I think the other way to approach the area becoming the volume, I think by some approximations, by some estimations, they will like cutting the functions one by one and making it solid. But I think that is not in the concept of the our solid. Oh yeah. I will tell you next Tuesday. Okay. I think